In this video, we're going to continue talking about chemical bonding, and specifically, we're going to be looking at lesson 1.2, where we're going to cover how to draw Lewis structures and how to identify the molecular shapes of those structures. So last time, we talked about lesson 1.1, where we reviewed some fundamental chemistry concepts, and the ones that are going to be most relevant today is going to be how to determine the number of valence electrons, because we need to be concerned with valence electrons when we're talking about bonding. And then you also need to be able to draw electron dot symbol. So those two things that we learned last time, we are going to use extensively today. Okay, so what are we going to do today? We are going to, again, revisit the octet rule that we briefly visited last time. Okay, we're going to elaborate on it a little bit more, and we're going to use that octet rule to draw Lewis structures of covalent compounds. So we will not be talking about ionic today. Everything will be about covalent structures. And then lastly, we're going to predict the shape around those atoms. Okay, so when we're talking about chemical bonding, we need to understand why it is that we even have bonding theories. Where did this come from? Okay. So the usefulness and application of bonding theories is that they help us predict how atoms are going to bond together. Okay, basically how compounds are formed. And it also can inform us on the combinations of atoms that can actually form a compound and the combinations that cannot. So for example, many of you are probably familiar with NaCl, which is an ionic compound. Here, NaCl exists as this formula and not NaCl2. Okay. Also with water, water exists as H2O and not as H3O. And why is that? Well, we're going to see today that that is inherent in the way that their valence electrons are arranged and in the number of valence electrons that they have. Okay. Bonding theories can also help us explain the shapes of molecules, and that allows us to determine many of their physical or to predict many of their physical and chemical properties, right? So from these concepts of bonding theories, that's basically what allowed us to be able to develop the concept of the octet rule and Lewis structures that we're going to talk about today. All right, so what is Lewis theory? It's a bonding theory, and it's actually something we talked about last time, where we defined that a chemical bond, now we are attributing this to the Lewis theory, where a chemical bond involves the sharing or transfer of electrons. Okay, sharing, again, this was for covalent compounds. Covalent compounds are the ones that share electrons, and recall that when an electron transfer occurs, this is going to be an ionic compound, right? Okay, so why do they share or transfer electrons? Well, that is in order to attain a stable electron configuration for the atoms involved in the bonding. What do we mean by a stable electron configuration? Well, this means that 8 electrons are now occupying the outermost or the valence shell. This observation is what led to the octet rule. Okay, so in chemical bonding, atoms transfer or share electrons to obtain outer shells with 8 electrons. Okay, so what this means is that these, let's recall the dot structures of this is all group 2 elements. Okay, so if you look at your periodic table and you look at the second row, these are all of the main group elements that are there. Okay, I've added electron dots here, representing how many valence electron each of these elements has. Okay? So the most stable configuration is going to be your noble gas configuration. So noble gas. When we say the most stable configuration or noble gas configuration, we are talking about the same thing. Okay. So what you'll see here is that neon is a noble gas. It's a group 2 noble gas or a period 2 noble gas. Okay, and it has 8 dots around it, meaning it has 8 electrons. And this is what we refer to as the most stable configuration. So that means that when atoms are bonding, they're trying to achieve 8 electrons around themselves. There is an exception to this octet rule. The exception is helium. If you look on your periodic table, you'll see that helium is a noble gas, okay? But it only has 2 electrons, and it also has 2 valence electrons. And basically, it is still a noble gas. So this means that for helium, 2 electrons in the outermost shell is the most stable configuration. We call this a duet. Okay? So it's an exception in terms of the octet rule, meaning we don't count 8 electrons to determine the most stable configuration, but it what we are saying is that helium is stable. It is still a stable configuration. It's just it's able to achieve that stability with just two valence electrons. Okay. So let's go ahead and create some covalent bonds. What do we mean by sharing electrons? All right, so let's start with hydrogen and oxygen. We're going to use H2O as an example here. So we're going to start with hydrogen and oxygen, and they have the following dot structures, right? So if we look at hydrogen in our periodic table, it's in the first group, so it has one valence electron. If you look at oxygen, it's in the sixth main group, okay? So it has 6 valence electrons. Okay, so hydrogen and oxygen, they're going to share their unpaired electrons, so that each hydrogen atom gets a duet and the oxygen atom gets an octet. So what does that mean? Well, I have a hydrogen atom here. This electron here can be shared with this electron that is by itself. Oxygen has 2 unpaired electrons. It's this one and this one. So hydrogen, with its 1 unpaired electron, it will pair up with this unpaired electron of oxygen in order to be able to satisfy its duet. Okay? The electron here of this oxygen, it'll go ahead and pair up with this unpaired electron. Okay, and when we do that, we basically get a structure like this, where now this electron here is coming from oxygen. This one is coming, that one. One electron in the pair is coming from oxygen, and then the other electron, for example, is coming from hydrogen. Okay, and this is what we mean by electron sharing. Okay, this electron pair here is being shared. This electron pair up here is a lone pair. It is not participating in the bond. So let's look at that a little bit more. So the shared electrons are those that appear in the spaces between the two atoms, and they're going to count toward the octet rule or the duet rule if you have hydrogen of both of the atoms, right? So you have duet, you have a hydrogen here on the left-hand side. You'll see that these 2 valence electrons there are now being shared by both hydrogen and oxygen. So what that means is that when I am looking at whether hydrogen has satisfied the octet rule, again, in this case for hydrogen is going to be a duet, you're going to see that it has 1 and 2 electrons around it. Now, if I were to count how many valence electrons are around oxygen in H2O, I would count 1, 2, 3, 4, 5, 6, 7, 8. So by hydrogen sharing its electron with oxygen and another hydrogen sharing its electron, oxygen has been able to achieve 8 valence electrons around it. So here, why is hydrogen satisfied with a duet? The reason hydrogen is satisfied with a duet is just as we explained in the previous slide, where helium, here's my noble gas helium, is satisfied with 2 electrons, right? So hydrogen is going to try to achieve the noble gas configuration closest to it. That's going to be helium. So when it shares electrons, it is actually going to be able to achieve the helium configuration, which requires only 2 valence electrons to be satisfied. So that's why hydrogen is satisfied with 2 electrons. Okay, so just some terminology about these Lewis structures. As we saw in the previous slide, these 2 where one is coming from oxygen and the other one is coming from hydrogen, those are going to be your bonding pair. Okay, that's your bonding pair there. The other pairs up here, this one, these are called lone pairs. They do not participate in making a covalent bond. So then in Lewis structures, once we have identified our bonding pair electrons, we represent those with dashes. That way it's easier to see which electrons are lone pairs. So these here are going to be lone pairs. And these dashes, they basically contain 1 electron from oxygen and then another electron from hydrogen. So each dash represents a pair of shared electrons, where 1 electron is coming from one atom and the other electron is coming from the other. All right, so here's a summary of that. I wanted to, again, throw some more terminology to make sure we are communicating correctly. So a molecular formula is going to show the number and identity of all of the atoms in a compound, but it doesn't tell you which atoms are bonded to each other, right? So things like H2O, C2H4, you know that there are some carbons in here, there are some hydrogens, there's 2 carbons, and there's a total of 4 hydrogens. But who's bonded to whom? And that's what we're going to be able to communicate with a Lewis structure. So with Lewis structures, a Lewis structure is going to be able to show you the connectivity, meaning what is bonded to who is bonded to who. Okay. So it's going to show you the connectivity between atoms, and it's also going to show you the location of the bonding and non-bonding valence electrons, and that's where understanding how to identify the shape of a molecule will come in. So first, let's focus on drawing the Lewis structure. So the general rules for drawing the Lewis structures are outlined here. First is going to be identifying the central atom, if applicable. That's not always applicable, and then in the first few examples, we will not have to do that. But in the later examples in this video, we will be identifying the central atom. Right. So then, once you have identified the central atom, if it's applicable, then go ahead and draw the dot structures for all of the atoms in your molecule. Okay. And then go ahead and identify your unpaired electrons, because these are the ones that are going to be forming the bonds. Then you can pair the unpaired electrons, and you do this to give every main group element an octet of electrons. And once you do that, you replace those paired electrons with a dash. And then the only exception to that octet rule is going to be hydrogen. All right, so let's draw some structures. So here, all of these examples here are going to be diatomic molecules, and we're going to look at more complicated molecules in just a minute. So first, let's say I want to know how two chlorine atoms would bind together. Okay, can they even form a bond? Well, so the first thing that I do, so if my formula is Cl2, okay, this is my molecular formula, and I want to show how it is that bonding pattern can be achieved. So first, I put down the dot structures, or I draw the dot structures of each chlorine atom. This is telling me I have 2 chlorines, which is why I'm showing 2 chlorine atoms here. And then I have placed 7 dots around it because it has 7 valence electrons. Again, recall that we only are concerned with the main group elements. So this would be main group 1, 2, 3, 4, 5, 6, 7. And chlorine is here, 7. And this would be 8, our noble gases. Okay, so chlorine has 7 valence electrons, which is why it has 7 dots around it. So now I want to pair, I identify my unpaired electrons, and I recognize that this one can pair with that one to create a more stable arrangement. And that is what I'm showing here. One electron is coming from the chlorine on the left-hand side, for example. Let's say it's this one. And then the other electron is coming from this other chlorine atom, which would be this one here. Okay. So once you have paired the electrons that are unpaired, now that they are forming a pair like this, you can now replace this bonding pair with a dash. And that is what is being shown here. So after any time that you draw any kind of Lewis structure, you always want to make sure that you have satisfied the octet rule for each atom. So let's look at the octet rule for the atom on the left. Here I have chlorine, and I have 1, 2, 3, 4. I'm actually going to use my laser pointer. So 1, 2, 3, 4, 5, 6, 7, and 8. All right, so again, recall that each dash is going to have 2 electrons, and the electrons in that dash will belong to both atoms. So the atom on the left-hand side has 8 valence electrons. Now let's look at the one on the right-hand side. So we're going to see that this one also has 8 valence electrons. So if we do 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's going to be 2 electrons in that dash, and they also belong to the chlorine on the right-hand side. So that means this one also has 8. And therefore, this molecule is one that exists because it is able to satisfy the octet rule, right? And it was able to form a covalent bond. Right? Let's look at hydrogen. Right? Each hydrogen, so the molecular formula for this would be H2. And so you start by drawing the dot structure for each one. So we are trying to draw the structure for H2. Right? So you start with the electron dot structure for each hydrogen, and then you pair the hydrogens by identifying the unpaired electrons. So those two can pair together. And now you just replace this bonding pair with a dash. Okay. And there you have H2, or hydrogen gas. All right, now let's look at oxygen. If we look at oxygen, oxygen is located over here. and therefore it has 6 valence electrons. And that's why each one has 6 dots around it. Here, the molecular formula is O2. So again, you identify the unpaired electrons. There's one here. That one will pair with this other unpaired electron. Then this pair here, and it'll pair with that one. And what ends up happening is that you end up getting 2 bonds here. You end up getting one bond in the top, where it's one of these pairing with the other, and then another bond here. So you can replace the pairs of each you can replace each pair with a dash line. And that's what is being shown here. One dash there and another dash here. And this is what we call a double bond. And in this double bond, you are going to have a total of 8 electrons here. So I want to redraw this with a different color. Let's do green, where the valence electrons, I'm drawing them like this so that you can see that there's one valence electron in each of those that corresponds to the oxygen, and then another one from the other oxygen. So that is why you have 8 electrons in that double bond. That's because each dash bond has 2 electrons in it. Remember, each dash represents a pair of electrons. Okay, let's do nitrogen. This is our last one here. Nitrogen is over here, so it has 5 valence electrons. That's why it has 1, 2, 3, 4, 5. So these are going to be my unpaired electrons in nitrogen. And then I have 3 unpaired electrons in the other nitrogen. So that means that this one can bond with that one, this one can pair with that one, and this one can pair with that one. So what you end up getting is a triple bond. Okay. So let's highlight this here. Right, so then you can replace each pair with a dash, which is what is being shown here. And this is called a triple bond. So again, recall that in each one of these bonds, there's going to be 1 electron there, and then another electron here, and that's what creates that bond there. And so each dash is going to have 2 electrons for a total of 6 electrons in that triple bond. Okay. All right, so let's do a few more examples. So these were all in the previous slide. These are all diatomic molecules. So we're just looking at 2 molecules and how they might bind. But of course, many compounds in nature don't just have 2 atoms. Molecules are going to have more than 1 atom generally. So here are some more examples. So here with methane, the molecular formula is 1 carbon and 4 hydrogens. It's CH4. Okay. So the dot structures that we would use to create these structures would be carbon with 4 valence electrons. Oops. And so you can use your periodic table to determine how many valence electrons carbon has. So carbon is going to have 4 valence electrons, and then the hydrogens have 1 valence electron. So here, because we have 4 different atoms, you do need to identify the central atom. The central atom here is going to be carbon. Whenever you have carbon, carbon will always be the central one. Okay, so this means that we have 4 hydrogens. There's another hydrogen with its valence electron. And basically what was done to generate this Lewis structure is that each unpaired electron of hydrogen paired with each unpaired electron of carbon. And that's how you get those 4 bonds. So your Lewis structure will look like this. And then your structure in 3D space doesn't exist as a flat molecule. It's actually going to have, it's going to arrange in 3 dimensions. And this is what we will be talking about next when we talk about the shapes of molecules. Right? But for now, let's just understand how these molecule Lewis structures were generated. So let's look at ammonia. Ammonia has 1 nitrogen and it has 3 hydrogens. What were the dot structures used here? Well, nitrogen, if you look at your periodic table, it's going to have 5 valence electrons. And then hydrogen is going to have 1 valence electron. And again, I know that nitrogen will be my central molecule because nitrogen having 1, 2, 3 unpaired electrons can make 3 bonds. So that means 1 valence of hydrogen will make a bond with that unpaired electron of nitrogen, and the same goes for the other unpaired electrons. And that's how you get a Lewis structure that looks like this. It's also why you have a lone pair up here. is because since nitrogen has 5 valence electrons, two of them are going to be paired. And then we're going to learn that NH3 looks like this in 3 dimensions. Right, lastly, water, we did this one already, it's H2O. Oxygen is going to have 6 valence electrons, and then each unpaired electron is going to bind with the unpaired electron of hydrogen. And this is why H2O exists with 2 hydrogens and 1 oxygen, and not with 3 hydrogens and 1 oxygen. We are going to later see in the course that that molecule actually does exist, but it's going to exist with a charge, and we will see why that is the case later. But as a neutral molecule, water exists like this. All right. This is just a summary of the common bonding patterns that you are likely to see in this course. As we mentioned in the previous lesson, since we are going to be dealing with organic molecules and with reactions in organisms like metabolic pathways, you're often going to see the hydrogens, carbons, nitrogens, oxygens, and some halogens. Okay. But these are going to be the main bonding patterns that you're going to see in this course. And so it is important that you recognize how these patterns are generated. All right, now let's wrap up with shapes. All right, this is the last thing we're going to cover in this video. All right, so molecular shapes is basically how we are able to describe the 3-dimensional arrangement of atoms in space. And the reason we do this is because this will be able to inform us how polarity is going to work, and then how intermolecular forces arise. Okay, so first let's focus on being able to identify the shape around the molecule. Okay, so we've learned so far that a Lewis structure can give you information about how the atoms are connected, but it does not tell you their shape in 3 dimensions. Right? So in order to do this, we basically communicate this as a way. So when we say that we're determining the shape, generally we're speaking about the shape around a given atom. This is also sometimes referred to as the central atom. And when we do this, we first determine how many groups surround the atom. Okay? And here, a group is defined as either an atom or a lone pair. And we will do some examples of this in a minute. Okay, the theory that we are using in order to generate these descriptions of the shapes of these molecules, that's called VSEPR theory. And all you really need to know here is that this is the theory that justifies us being able to assign the shapes we're going to talk about in just a minute. And the other thing to note is just that this tells us how the groups are arranged, because the theory tells us that the groups will go as far away from each other as possible. And these groups, again, it includes the lone pairs. So oftentimes you're going to see that lone pairs will congregate together. And this is the theory basically that justifies that, or that describes that. But beyond that, all we really need to be able to do is read this chart, okay? Because this is how we will be able to assign shapes to molecules. Okay. So the first thing to notice here is that you want to be able to always locate your central atom. That is the first step. So what do I mean by that? Well, in this first molecule here, nitrogen would be the central one, because everything is bonded to nitrogen. Boron here is another one, oxygen, and so on. Okay, those are going to be what we refer to as the central atom. Okay? Now the axes are going to describe what is bonded to that central atom. So here in your y-axis here, when we talk about electron groups, really what this means is the number of atoms and lone pairs that are surrounding that central atom. So if we look at this first molecule up here, we see that we have 1 chlorine atom, 1 oxygen atom, and 1 lone pair surrounding that central atom. So for this reason, this has 3 electron groups, and that is what this 3 here means. If we look at this H2O molecule down here, we'll see that there are 4 electron groups surrounding it. Hydrogen, there is 1, 2, this lone pair 3, this other lone pair is 4. So it has a total of 4 groups. And that is how you read the y-axis of this table. Now, we can also make an additional distinction. That's going to be the y-axis. I'm sorry, the x-axis, or this top row. Okay, this is what we call ligands. All right, and here what ligands are referring to are only the atoms that are bonded to that central atom. So for this first molecule here, we have 1 and 2 atoms surrounding that central atom. The lone pair here doesn't count. And that is why it is located here in this column. For water, we can do the same thing. 1 and 2 atoms, the lone pairs don't count, and that is why it is located here. So the shape of these molecules are written down here. We have bent, trigonal planar, another bent, but it's a different type than the top one, trigonal pyramidal, tetrahedral. And these are the ones we are going to use most often in this course. Use most often. Okay. The other ones are here for your reference in case you see them in some word problems, you know what they're referring to, but you won't need to memorize those in the bottom. However, you will need to memorize these shapes here for this course. All right, let's go ahead and apply this so that we can understand how to read this table. Okay, so what is the shape of the following molecules? So I'm going to walk you through what it looks like from the beginning of generating your Lewis dot structure to then being able to identify what kind of shape it has. Okay. All right, so in A, the first thing that I notice is that I have more than 2 atoms. So what that means is that I first need to be able to identify the central atom. I see that I have a carbon. Carbon will always be the central atom. So that means I have 1 carbon, and then immediately I go ahead and write the valence electrons that it has. Again, recall carbon is here, so it is in the 4th group. Okay, so it has 4 valence electrons. The other atoms are going to be hydrogen, which has 1 valence electron, it's here. And then I have chlorine, which has 7 valence electrons, and it's over here. All right, so now I identify my unpaired electrons. I see hydrogen has 1, carbon has 4, so it can make 4 bonds. Chlorine has only 1 unpaired electron, so it can only make 1 bond. Okay. So what this means is that this hydrogen will go here. I have 2 hydrogens in this molecule, so I'm going to go ahead and draw another hydrogen. This is going to form a bond there. Chlorine has 1 unpaired, it can form a bond there. And then I'll draw in my second chlorine that is part of this molecule, and I recognize these 2 can bond together. So what this means is that my Lewis structure can look like this. But now what we want to do, well, before you continue, you always want to make sure that you have satisfied the octet rule. Your Lewis structure is not complete until it has these valence electrons in there. Don't forget them. Okay. So now how do I know if I have 8 electrons or if I've satisfied the octet rule? I look at chlorine and then count all the electrons around it. 1, 2, 3, 4, 5, 6. And then in this dash, there are 2 electrons, 7, 8. So this chlorine has 8. This chlorine will also have 8. If we look at hydrogen, hydrogen has 1, 2, which is just in this bond. And again, hydrogen is the exception where 2 valence electrons satisfies the octet rule. Okay, so we've drawn our Lewis structure successfully. Now what we want to do is determine its shape. So the first thing I do is I count the number of atoms and lone pairs surrounding my carbon atom. So I see that I have 1 atom, 2 atoms, 3 atoms, 4 atoms, and no lone pairs on carbon. So that means that on my table, I am going to be looking at structures here in 4, because I have 4 electron groups. Okay. Now I'm going to determine how many ligands I have. So for ligands, I'm going to count only the atoms. I'm going to disregard any lone pairs that are surrounding the carbon. And again, I see that I have 4 atoms surrounding it. So this is a case. So I have 1, 2, 3, 4 atoms. This is the case where the number of electron groups and the number of ligands is equal. So that means that I'm going to be looking at 4 ligands, and therefore this is the structure that I am looking at, and the shape of this is going to be tetrahedral. So one of the things that you want to know with this table here, I'm just going to move back, is that your dashed, the solid dashes, what that is communicating is that this molecule is pointing towards you. Sorry, not solid dashes, but solid wedge. Solid wedge. That means it's coming out of the paper towards you. The dashed line means that it's going away or into the paper. And then the solid lines means that it's just on the plane of the paper. Okay. And we will look at some molecular model kits when we do the lab this week. You will be seeing how this is actually, how it actually looks in space. All right, so what this means is that the shape of this is actually tetrahedral. So I can redraw it to try to communicate that. And usually how we do this is we draw it like this. Okay. So now this is a Lewis structure that takes into account the shape, and specifically it's a tetrahedral. All right, let's do the next one. Here we have CH2O, right? So here we have carbon is going to be the central because carbon is always central. 1, 2, 3, 4 valence electrons. Then we have oxygen. Oxygen is here. It has 6 valence electrons. 1, 2, 3, 4, 5, 6. And then hydrogen, as we've already seen, is going to have 1. Okay. So again, each hydrogen can pair with the single one, electron of carbon. For oxygen, I see I have 1 valence electron that's unpaired, another that's unpaired. That means this one can form a bond there. And then with that remaining electron, I can form another bond there. So what this means is that I have this kind of structure. And then carbon is double bonded to oxygen. And then I have my lone pairs. All right, so now let's think about the shape of this one. So how can I identify what kind of shape I have? Well, first I need to look at the number of atoms and lone pairs in the central carbon, in the central atom, which is carbon. Here I have 1 electron group, 2, 3. So I'm looking at this part of the table. Now let's look at how many ligands are bound. Well, that's going to be the same thing because I just have 3 atoms bound to it. So that means I'm looking here. So because of this, the shape of this molecule is going to be trigonoplanar. And then in order to communicate that, we often draw these structures like this, where it communicates that this is a trigonal planar. Trigonal planar. That this molecule has a trigonal planar shape. Right. Let's do 2 more. Again, we start by identifying our central atom. Here we don't have a carbon, right? But we can still identify who is likely to be our central atom. Okay. So sulfur, you're going to notice it's here. It is in the 6th group, and so it has 6 valence electrons. Fluorine is here. It's in the 7th group, so it's going to have 7 valence electrons. You'll notice all of your halogens have 7 valence electrons. Okay. So once I identify my unpaired electron, I can see fluorine can only make 1 bond because it only has 1 unpaired electron. Sulfur can make 1 and 2 bonds because it has 2 unpaired electrons. And so what that means is that sulfur is likely to be my central molecule because it can form more bonds than fluorine. So what this means is that fluorine will probably bind here or bond there, and this will form a bond here. Okay. Right, so that is what my Lewis structure would look like. Now let's determine the shape. Well, first I need to count the number of atoms and lone pairs around my central atom. So that would be 1, 2, 3, and 4. So I will be looking at this part of the table. Okay. Now I need to look at how many atoms are bonded. Right, so atoms here, that is going to be fluorine here, and this fluorine here. The electron, the lone pairs don't count. So that means I have 2 ligands or 2 atoms bonded to the central atom. So what that means is that we are looking at a bent shape. So in order to represent that, I would draw this as with sulfur in the center, my fluorines pointing down in a bent fashion, and then my lone pairs would be up here. And this communicates that this is a bent structure. All right, let's do our last one. This is 2 carbons and 6 hydrogens. So what this means is that I have carbons, again, they all have 4 valence electrons. My carbon is my central atom, but now I have 2 of them. What does that mean? Well, that just means that they are still going to be central in binding everything else or bonding everything else. So what that means is that carbon and carbon are likely to bond to each other because the hydrogens have just one valence electron. And there are 6 of them. So 1, 2, 3, 4, 5, and 6. Okay. So that means that carbon and carbon are likely to bond each other. You will often see this in the organic chemistry portion of this class. And then each hydrogen is going to bind one time or bond one time to carbon. It'll form one bond. So what this means is that our Lewis structure, I'm just rewriting it so it looks better. It looks like this. So now when we talk about shapes in a molecule like this that has more than one central atom, you could look at it that way, we talk about identifying the shape around a particular carbon. So in this carbon here, if I want to know the shape around this carbon, I would do the same process. I count the number of atoms and lone pairs around this carbon here. So that would be 1, 2, 3, 4 groups. Okay, so I'm still looking at this here. And then my ligands, or the number of atoms, is also going to be 4. So that means this is going to be, it's 4. So the shape around that carbon is tetrahedral. And then you can do the same thing for the carbon on the right-hand side. So this carbon here, it also has 4 groups around it. Okay, so this one is also going to be tetrahedral. All right, so that concludes everything that I wanted to talk about in terms of drawing the Lewis structures, using the octet rule to make sure we bond things correctly, and then also to predict the shape around a particular atom in a molecule. Okay, so depending on how many atoms and lone pairs are bonded, okay, that will determine the shape of your molecule. So next time, now that we are equipped with being able to draw Lewis structures and identify the shape, we will then be able to talk about bond polarity. And then that is going to inform us on what kind of intermolecular forces are present in your set of molecules. And that is what we will be talking about next time.